Hi there, welcome back to the Formulaic Approach channel. Now in today's video, we are going to deal with circular motion. Now we're going to deal with what circular motion is, terminology used in circular motion. Then we are going to do some basic derivations, basic derivations of formulas. Now, knowing that derivation is not as essential as knowing how to use the formulas we derive. But of course, what the derivation I will do help you to do is to understand the origin of those equations, or more like to understand how the equation functions, so that by the time you see a question, you can know whether or not a particular formula is deemed suitable for that equation. Is that clear? So do well to stick with me till the end. I'm going to solve questions by the end of these videos. So don't worry, we'll solve O-level questions down to advanced level questions. All right, let's go to what circular motion is. So, of course, you can already tell that circular motion is just motion in a circular path. I like to demonstrate what circular motion is to you. So look at this guy that is attached to my ID card now. This ID card attached to this rope rather. So if I swirl this thing around like this, so you're going to see like this. Now this guy here, provided that this string is this string, let's think of it as a string now, is inextensible. This guy is going to maintain a regular path that is circular, as it's going like this. Now, of course, I could decide to move like this, and I could decide to move like this. We are going to deal with both conditions later. But first, understand that this body here that is attached to this end here is engaging in circular motion. So if I were to draw the motion of that body, it will look something like this. So it means that the body, that guy is moving around this circular path. All right, this circular path. Mine is not circular. Circular path. Let's manage this one. Okay, so that body, let's say that body is here, for example. So it's moving in this circular path. It keeps going round and round and round and round. So now, a circular motion is basically motion around a circle. Motion about a fixed point. Motion. So we can define circular motion as motion about a fixed point called the axis. We call that fixed point the axis. So that fixed point will be a point at the center. For the case of what I was swirling, then that my hand will mark the axis of rotation of the object. Now, so motion about a fixed point or axis, that is circular motion. Now, there are so many things that we have to know about this circular motion. Before we analyze those things, let's first talk about the terms we are going to hear as we talk about circular motion. Now, the first term that you will likely hear, and this is in no particular order, but I just like to start with what a cycle first is. A cycle or a revolution. Now, a cycle is simply a complete motion around a circle. So, if I move this body this way, 1, 2, 3. Now that counting of 3 means I completed 3 cycles. That is, if it's coming from down, I'll go 1. So this is 1 cycle. 2, that is second cycle. 3. So motion from the starting point back to the starting point at a regular path is going to be a circle. So a complete revolution is a cycle, all right, a complete 360 degrees or 2 pi radians. Now, you have to understand this. 2 pi radians or 360 degrees is what we have in a circle. So that is what a cycle is. All right, the reason why I use the term cycle is, after this video, we'll talk about simple harmonic motion, and you're going to understand the relationship between them. Now, the next thing you have to now understand is the period. I like to talk about the period next. Now, the period is denoted by T. Now, the period is the time taken to complete that one revolution you saw there, that one cycle, okay, that one cycle, the time taken to complete it is the period, okay, time taken to complete a revolution. So it's defined in mathematics or mathematically as the time per number of revolutions. So for example, as I did that thing, I think I rotated it 3 times. So that 3 times is the time taken to complete that 3 revolutions will be the total time, okay? So if I did that 3 revolutions in 8 seconds, or maybe 5 seconds, so that will be 5 over 3 revolutions. I did 3 revs. Okay, so 5 divided by 3, that will be 1.67 seconds. So what this 1.67 seconds means is that I took 5 seconds to complete 3 revolutions. It means each revolution was completed in 1.67 seconds. Do you understand that now? That is, each cycle was completed in 1.67 seconds. So that is what period is. Period is the time per revolution, the time per revolution. Now it's different from time. Time could be the time before a complete revolution, or time could be describing the time for the total number of oscillations or total number of revolutions covered. So that is time. Time is quite arbitrary, but period is specific. Period is just the time for a cycle. All right. Now the next term, so it's measured in seconds. Measured in seconds. Now the next term is frequency. I'd like to explain frequency next. Now frequency is denoted by F. Now in some textbook, period is denoted by P, okay? So for frequency is now the number of revolutions you are able to complete per time, per unit of time. Number of revolutions per unit of time. So mathematically it will be defined as number of revolutions per unit of time. Now what do you notice? You notice that it is just the reverse of period, right? The inverse of period. So that is why F is given as 1 over T, capital T. So for that revolution that I did 3 revs in 5 seconds. 3 revs in 5 seconds. So this will be 0.6. Now what's the unit of measuring frequency? Now since it is, now the unit is actually hertz, named after Frank Hertz, but we denote it by Hz. So for this my question, this will be 0.6 Hz. Now, but because frequency is also inverse of period, it has another unit. Is either I write it this way, 0.6 Hertz or 0.6 per seconds. Is it clear? All right. So that is frequency. Frequency is the inverse of period. So, and if you discover, if you take 1 over this, you get 0.6 as well. And let's go to the next one. Number 4. Another terminology I would like you to know is the let's talk about, we know frequency now. Let's talk about angular frequency or angular velocity, as you might see. Now, the angular velocity is the speed, the angular speed of the body across the circular path, along the circular path rather. The angular speed, the rate of travel, that's angular velocity, the rate of travel of the body along the circular path. Now I'm going to show you some derivations from here now. We'll begin some derivations from here now. Now, we already have, we know that, so I told you the angular velocity, just like velocity. What's velocity? That's the change in distance, displacement over time. Change in displacement over time. That is, so angular velocity is going to be what? Change. Angular velocity we denote it by, denoted by omega. That's like a W with one side covered. So angular velocity is going to be the change in, if normal velocity is change in distance or displacement over change in time, or either way you could just say S over T, then we know that angular velocity will be changing angular displacement, because in this case we are not covering linear distance, we are covering what? angular distance. So this will be angular displacement. Angular displacement. So angular displacement is denoted by what? By theta. So change in angular displacement over change in time. Okay, over change in time. So if this be the case, then I can say that omega is equal to theta over time. Now recall that this time is not period. This one is time taken to complete a path, a particular angle, a particular distance along the circle. So for example, let's begin our derivations. Now let me now begin to analyze this circle for you. If this body started from here, for example, so it started to move from this point and got to this point, this body has covered, now we could say here, we call it the circumference of the circle, right? It has covered a part of the circumference, rather, a fraction of the circumference. Now, I now told you that the speed along this path, now it has also in angle, we can also say that it has covered an angle theta. So this is the angular displacement that it has covered. It has covered angle theta. So the angular velocity we said would be what? Theta over t. Now, let's now do some derivations. You know with me or agree with me that this fraction of the circumference is called an arc, right? The fraction of the circumference is an arc, a part of the circumference, some distance along the circumference is called an arc. So we can use the mathematics that the length of an arc, in this case we call that length s, is just a distance s. It could be here too, it could be from here to this place, it's also distance s. Is that clear? So that length of an arc is a fraction of an angle out of the total 360 degrees times the entire out of the 2 pi r. I don't know if you understand. Fraction of the length. Is that clear? The fraction of the length. So this is what we have, okay? Now before I introduce this, let me show you some other things that could happen here. What if we now cover the entire 360 degrees? If we cover the entire 360 degrees. No, before we do that, in fact, let's change some things here. You know, I told you that 360 degrees is 2 pi. Let me do the altering here. So S can be theta over 2 pi, therefore, times 2 pi r. 2 pi r. So 2 pi can take care of 2 pi. So that S equal to theta r. You must have seen this in mathematics. Okay, so this will be like if I call this my equation 1, because I need this, so I don't need this, so I want to use this. Equation 1, let's call this equation 2. This will be my equation 3. So just make sure you're following me. Now, if this is the case, then I can begin to derive things here. I can also say that from here, theta will be equal to omega t. So if theta is omega t, then here can become S equal to omega t r. And tell me, when do I need this formula? You need this formula when you are given the angular distance, the time, the angular displacement rather, the time and the radius of the circle. Then what do? You have to calculate the displacement, the linear displacement. Now, what if, now from here, what if what I covered was the entire circle? If what I covered is the entire circle, what will be the angular speed? The angular speed will now be equal to what? Angular velocity rather. Now you see me use angular velocity and angular speed interchangeably. I'll tell you why. So just stick with me. Now, omega will be, theta is now the entire circle, that's 360 degrees or 2 pi radians. Now what will be the time taken to complete the circle? Is period. I already told you that, right? So that will be over t. Does this make sense now? Good. So from here, mathematically speaking, this omega is equal to 2 pi times 1 over t. You know, 2 pi times 1, 2 pi. T over 1, t times 1, t. So I've not changed anything. But recall that 1 over t is what? Frequency. Therefore, I could say that omega is equal to what? 2 pi f. Does that make sense now? So let's call this equation, if this is equation 4, this will be equation 5. Now let's move further. Let's see if we can alter other things from here. Then you tell me, when do I need this formula? When you are told to find the angular speed and you are giving the frequency, you'll be giving only the frequency in this case, only the frequency. and you just plug into the equation, you're able to get your angular speed. Now, one thing you must know about angular speed, or angular velocity rather, is that it is constant everywhere in the cycle. The angular speed is constant for a particular circle. Is that clear? But it decreases with the radius. It decreases with radius. Here's what I'll do. I'll show you a relationship between linear speed, those linear quantities and the angular quantities that we use to analyze this guy. I'm going to show you the relationship. All right, but let's go on further first. Now, there's something called, of course, if the body has speed, so it is possible if the speed changes, then the body will have acceleration, because acceleration is the change in speed of the body over time, right? So now, does the speed of this body change? Now, I just told you that this angular velocity is constant. Yes, angular velocity is constant, but not linear velocity. Now, this body also has linear velocity. So the linear velocity of this body is not constant. Now, how do I know it's not constant? The value of the linear velocity is constant. So we'll say that linear speed is constant. You know that speed and velocity are not the same. Speed is without direction. Velocity has direction. So the linear speed of this body is constant, okay? Everywhere the value is not changing. It is going 2 meters per second. It's going 2 meters per second. But what will change is this. Watch this. At this point, let me redraw this circle. At this point here, the linear speed, no, let me show you some before I prove that. See, by yourself, notice this. As this body is going like this, for example, if this body were to cut off, for example, now how would it move? It will move straightward in the direction where it is cut, right? In the direction of the parts of the cycle that it got to. If it's going like this and the cutting happen at this direction, it will move up. If it was going like this, it will move this direction. So what I'm trying to say in essence is that it always moves tangentially. The velocity is always directed tangentially at any point along its motion. So given that this body is moving, let's say it was moving in this direction, clockwise. It is moving clockwise like this. Then this is my body. The velocity at this point, if I pick this point, will be tangential to that point. The velocity at this point will be tangential to that point. The velocity at this point will be tangential, tangential, tangential at every point on my circle. Is that okay? So it means that as this body is going like this, if it gets caught around at the time it got here to this point, it will move away like this. Do you understand? If it gets caught at this point here, if it gets caught, if the rope gets caught, the rope that is, is rotating with, if it gets caught at this point, at the point when that body got here, it will move in that direction. So, and that's because of the velocity has direction. So what do you notice? The direction is constantly changing. This direction is different from this direction. Makes sense? So if the direction is constantly changing, then the body is actually accelerating. So that's why we call it linear velocity, or we call it velocity. Okay, we call it velocity, not just speed. But the value is linear speed, okay, or angular speed in value. But of course, we have said that angular velocity does not change. That is linear velocity that changes. Why? Because the direction changes. Now, what did I say? I said that this linear acceleration now, linear acceleration, and I'll show you that there's a relation between even linear and angular acceleration. So maybe we should start with that. Let's start with angular acceleration. I've not talked about linear. So let's first talk about angular acceleration. Angular acceleration. Now, what is angular acceleration? Angular acceleration is going to be changing angular speed over changing time. Angular acceleration, we denote it by alpha. So alpha is equal to omega over changing velocity over time, right? So angular acceleration will be changing angular speed over changing time. Does this make sense now? All right, so we can derive things from here. You know that omega is theta over t, right? So alpha can also be what? Theta over t squared. Okay? So, you can just do your thing. All right, but this is not where I'll get into. So we know that this exists, right? And you can write it in terms of, say, the way we use calculus, that changing this, the omega dt. Okay, so that this one will become d theta dt squared. All right, d squared theta dt squared. D squared theta dt squared. Okay, so that's that. That's that. Now, let's now get, so we have angular acceleration. Now, let's now get to the relationship between them now. Relationship between linear velocity and acceleration and angular velocity and angular acceleration. So what is the formula for linear velocity? Linear velocity, v is change in distance over change in time, right? So I can write it as v equal to s over t, like you rightly know. So if v is equal to s over t and s is theta r, s, recall that from equation 3, that s is theta r, so v is equal to theta r over t. But of course, look at this, theta over t, that is omega. So v can be said to be omega r. Okay, if this is equation 5, let's call this equation 5, this will be equation 6. So can you see the relationship between them? I want to show you something. Just watch this. Now, what will the angular acceleration be? What will be the relationship? What is acceleration normally? This is linear, this is linear. Linear, v is linear velocity, omega is angular velocity. A is linear acceleration, alpha is angular acceleration. What's the formula for linear acceleration? Is change in velocity over change in time, or I write as v over t. So what is A equal, what is V? Now V, we just got V to be omega R, right? V is omega R here. So omega R over T. Now what is omega over T? Omega over T is what? Alpha. So angular acceleration is equal to what? Alpha R. Is it clear? Now you now ask me, Master, well, when do you need this formula? Okay, when you need this formula is, you are told to find linear acceleration. We are giving angular acceleration and the radius of the circle. Then you'll be able to find linear acceleration. So what do you notice? You should notice this, that if I'm looking for linear displacement is angular displacement times radius. Are you seeing the relationship now? If I'm looking for linear speed will be angular speed times radius. Are you seeing that? Okay. If you are looking for acceleration, linear acceleration will be what? Angular acceleration times radius. Do you see this? All right. So this is the relationship between all of them. Now let me show you something again. Now, if just in case you now have to calculate those dynamics that are associated with motion that we have discussed before, and if you have not seen my video on that, do well to see it. Okay. So do well to watch that video on motion, kinematics. I dealt with the kinematics from this thing. What's it called now? From the scratch, velocity time graph, horizontal motion, vertical motion, projectile on an inclined plane, motion on an inclined plane without the dynamics. Okay, we are not dealing with I didn't deal with dynamics, and I'll show you this video on the dynamics too. But go and see that video. It's going to help you to understand this thing. So if you have seen that kind of video before, or at least you have seen this formula, you would have seen this formula before. We have dealt with motion, which I assume you have. You would have seen that V equal to U plus AT, and that S equal to UT plus 1 over 2 AT squared. You'd also have seen this before, that S is also equal to U plus V over 2T, and that S of V now, V squared, is equal to U squared plus 2AS. Now, if you want to discuss circular motion using this guys too, let's say you are told to find, or given the formal velocity and all that, the changes that this equation also apply to circular motion. You just be making different changes, little changes rather. In this case, V is final velocity, U is initial velocity. For angles, for circular motion, V, which is final velocity, will be omega F. Let's put omega F as final. V and U, which is initial velocity, will be omega I. Okay, so in that case, my formula now becomes omega F is equal to initial velocity, which is omega I, plus AT. Is it clear? No, not A. A is linear. Now, A will be angular. So that will be alpha T. Is that clear? Alpha T. Now for S, let me give you enough space. I think it's longer. Now S will now be angular displacement, right? And what is angular displacement? S will be what? Theta. Angular displacement. So that will be theta is equal to initial velocity U, omega I times T plus 1 over 2 alpha T squared. Is it clear now? For this one too, angular displacement is still equal to omega I plus omega F over 2 multiplied by T. And the last one, V squared, that is omega F squared, omega sub S, equal to omega sub Y squared plus 2 alpha theta. Is it clear? So you see that the equations have not really changed much. Okay, it doesn't even change. It's just the parameters that we altered a little bit, okay, in their forms. All right, now let's now deal with a little bit of dynamics now. What are the dynamics of circular motion? The dynamics of circular motion. Now we will soon solve questions, so don't worry. We'll solve questions. Just wait till the end of the video. We'll solve questions. Because someone might be thinking, when will this equation be applicable now? When will these formulas be applicable? Now, let's deal with the dynamics of circular motion. Dynamics is just the aspect that deals with the forces and all. So we'll do both together, fluid dynamics and the kinematics. Okay, but for now, I want to introduce the dynamics. Now, when the body is moving a circular path, okay, if the body accelerates, we said the body has acceleration, right? If the body has acceleration, what causes the body to accelerate? It is what? A force, okay? So if a force causes a body to accelerate, therefore a body moving a circular path is also under influence of a force. So, but in this case, which force would that be? That would be called, what is called the centripetal force. The centripetal force. It is the force that draws it towards the center, that draws the body towards the center. But then again, someone might now say that I've ridden a merry-go-round before and I'm not feeling attracted towards the center. In fact, on the contrary, I'm feeling like I'm going to be thrown out of that circular path. Yes. Now the reason is because of what is called frame of reference. Now let me explain frame of reference to you. Now you see, frame of reference is basically the perspective of the person. So for example, if I raise my hand like this now, if I'm looking at a mirror, I'll be raising my left hand. I'm raising my right hand here, but to be raising, because the perspective has flipped. So if I say I'm going like this to you now that is watching, if I'm going like this, which direction am I going? To you, I am going leftward, but to me, I'm going rightward like this. This hand is going rightward. Do you understand now? So the point is this, that the frame of reference is what changes it, what makes it feel that way. Your centripetal force is the force that actually draws it towards the center. But you that are in the merry-go-round, if you have reading this thing before, you must have reading it before. So you come here, you see something that looks like this. So you and your big head, you sit here. Then your other friend, who also has a big head like you, will sit here. You know, then one of the third friend will also sit here. Then the person will be pushing you around, well, like a roller coaster, you know. Those things, the force you'll be feeling is what is called the centrifugal force. Centrifugal, because you are in the system, so your frame of reference has changed. So centrifugal force is a fictitious force, a false force, a force that doesn't exist. Is that clear? Centrifugal force does not exist. It's a false or fictitious force. So, but that's the force that is making you feel as though you'll be swung out of that circular path around which you are moving. But the force actually that is acting on that body is the force that propels it towards the center, that moves it or draws the body towards the center. And that force is called what? Centripetal force. For the purpose of this video, I like to call it F sub c. Exactly. So we already know that net force causes acceleration, right? So F net is what causes acceleration. And we such that as the force applied on the body is very proportional to the acceleration that is produced, right? Given that the mass is constant, right? So F equal to ma. F is equal to ma. Now it has been seen that the acceleration of a body in a circular path is equal to omega and is equal to v squared over r. Then ask me, Master, how? Okay, I'm going to do the derivation of this for you, but I've done it before. So in case you don't understand this, what I want to derive here, just do your thing, like just, there's a simple way I can even derive it. Let me show you something. Or should I derive? Yeah, let's derive it quickly. Now, the acceleration of the body at a particular instance, if the body moves from here, I just like to start from this right word to this point here, for example, to this point, start from here to this point. Now, let me clean these lines that I drew. The body came from A to point B. Now, if I want to parameterize the distance moved by the body, I'll parameterize it in terms of a particular x-axis, x displacement, and y-axis displacement. Okay, so I like to use the x-axis, for example. If I use the x-axis, I'll parameterize like this. Let's say the body has gotten here. So the acceleration at that point, let's see it. So that body has moved a particular x and has moved a particular y. Make sense? So I said I like to use x. So let's call this angle theta. If that's angle theta, this place here is going to be our radius for the circle. Make sense? So if I compare these two together, I said I like to use x displacement. That is the displacement from x-axis. That's what we want to do. Okay? What's the displacement from x-axis? X is going to be, what relates, we know we have the radius. So what function relates this side and this side? That will be adjacent and this. So that will be cosine of theta. That will be adjacent and hypotenuse. Adjacent in this case is x. Over what's the hypotenuse there? R. So x therefore becomes r cos theta. Now recall from the equations we derived that theta is equal to omega t, from omega being theta over t, because multiply you get omega equal to theta over t. So I could say that x is equal to r cos theta and r cos omega t. Remember, this is my what's it called now? Angular, this is my displacement from the x-axis. So if I want to get my speed, what's formula for speed? I'll differentiate. Speed is this change in distance or change in displacement over time, right? So it means I'll take dx dt. If I take dx dt here, I differentiate this, r is here, I differentiate this with respect to t to remain only omega, dot differentiate cosine of an angle. The cosine of an angle will give you negative sine of that angle. Okay, so this multiplies this and we have dx dt, which in this case is velocity, is equal to r omega negative r omega sine omega t. Is this clear? So from here, if I bring this here, I know that to get acceleration now, I will differentiate my v, dv dt. And v is what? So it means I'll be differentiating this since this is v. That will be d minus r omega sine omega t. Okay? Omega looks a lot like w, but don't confuse them, okay? So acceleration therefore becomes the d's dt. So we have minus r omega. The derivative of sine of something is cosine of that thing. Cosine omega t. Yes, like that. Cosine omega t. I'm sorry. Differentiate this place first. The function first in front. Omega will remain omega, right? Then now differentiate sine of that thing. Will now give you cos of omega t. So A therefore becomes R negative R omega squared. Negative R omega squared cos omega t. Cos omega t. Now here, if you look at this very well, look at something. I want you to see something. If I do this, A equal to negative omega squared, I want to write R cos omega t. This R cos omega t was what I started with, is equal to X. So A is equal to minus omega squared X. Okay? So if my X is so long enough that is equal to the radius of the circle, at which point the body is traveling at the maximum maximum acceleration, or the body is for such a body to be traveling at the radius. You know this body now, this X is not for this body that is in a circular path. For a body in a circular path, this X will not reduce in its value. Actually, it shouldn't reduce in its value. What you should do is watch that my video on the derivation. It's longer than this, okay? But I want you to just try to eyeball this. You notice that it is R radius times omega squared, right? So let's say where that X is equal to the radius, is exactly equal to the radius, then my A equal to what? R omega squared. Now you see I've also eyeballed the negative. Reason being that this negative only shows you the direction. It only shows you that the direction of the motion of the acceleration of the body with respect to the body is opposite the direction of the pull of the body. The body is accelerating inwards, but the body will be feeling as if it's going outward. Exactly. So my point is now this, that this proves, now let's now use it to prove this. From here, even from here, you see that I've proven that velocity is R omega. If this is 90 degrees, sine 90, that's 1, R omega, which was what we proved here, V equal to R omega. Do you understand now? So from here, I could say that A is R omega squared. Since A is R omega squared, then, and V equal to R omega. So this thing means A equal to R omega dot omega. This is V. So A equal to what? V omega. And from the same place, from this same place, omega is equal to V over R, right? So if that's the case, then A equal to V dot V over R. So A equal to V squared over R. Exactly. So I hope I've been able to prove it shortly. That this just shortly, to prove it shortly. But I'll link that video in the description where I already proved that case. But let's go back to the dynamics we were talking about. Now what? I know that F is MA like we said, and A we just proved is V squared over R. So since we have proven this, then F is equal to what? MV squared over R. Let's call this equation. I've stopped keeping track. So let's call this one equation 7, so like equation 8. Okay, so since we also saw that A is R omega squared, then F equal to what? MR omega squared. That's another equation, equation 9. All right, so that's the centripetal force for you. That's the centripetal force. Now, but there are two types of circular motion. Types of circular motion. Okay, now let's deal with the first one, which is the vertical circular motion. Let me just use CM for circular motion. Then we'll deal with horizontal circular motion. Now for vertical circular motion, this is vertical circular motion that I showed you at the beginning of this video. When this body is moving like this is vertical, right? Vertical. Actually, my own is It has an extensible string, that's why you might be seeing it going, but if it had no extensible string, it will just go in a regular circular path like this. So this is horizontal circular motion. Now, if there's horizontal circular motion, what are the dynamics of that horizontal circular motion? It is what we discussed the other time. But I want you to see something to this now. Watch very carefully. Now, when a body is on a string, when an object is on a string, what is the force that is going to act on that string? It's going to have what? The force is what? Tension. Don't forget, any string body, we are told to discuss the dynamics of that body. On that string, you must talk about tension because the force on that string is tension. Then ask me, how do you know that tension is on a string? Okay. Let me ask you, if I suspend this body here, if this rope, this object were heavy enough, for example, and I suspending it, and I cut it at, maybe this is the load here, and I cut it near the load will of course drop. But where will the rope go? You will notice that the rope will go up a little, right? Now if the rope went up a little, then it means it accelerated upward, right? So it means a force caused it to accelerate upward. So it means a force was actually pulling it up, right? So what's that force called? It's called tension. Do you understand now? So that's tension. So at each point in time now, the centripetal force here will be the total sum of forces acting on the body. So if we suspend the body on a string like that and we start rotating it, that body will have weight, right? There will be weight on the body. So there are two positions we like to analyze. Every other position is also is not as easy. Okay, that's why we'll just analyze this horizontal position and vertical position. So let's go in this order: A, B, C, and D. So now at position, the easiest one is this position A and position C. At this position C, let's say our body is here. So at position C, our body is here. What will happen? The weight of the body will act from the center of gravity or center of mass downward. Weight always acts downward. I've told you that before. So W equal to what? Mg. So if that be the case, then how about what force will be acting in this direction? The force that will be acting in this direction is going to be tension because the body is at this position. The body is going around in this position. The force will be that will be acting downward. Inward is going to be what? Tension. So tension and weight are perpendicular. So weight does not have anything to do with its centripetal motion. Do you see that now? It's only tension that has something to do with centripetal motion. Why? Because centripetal motion always acts inward towards the center. I hope I've said that here. Centripetal force is the force that is drawing that body towards its axis. Okay? So in this case, at point C now, the same way will be for point A. So we say at points A and C, the centripetal force is going to be the tension. Okay, so we can therefore say that tension at point A and C is going to be the centripetal force mv squared over r that we just derived. Is it clear now? All right, let's call this equation 10. Now, how about at point B and D, the dynamics quite changes a little. So at point B now, for example, at point B, let's see what happens now. At point B, the rope is up. Now, where will the weight act? Straight down, like I said, straight downward. Weight is mg. Now, how about the tension? Where will it act? Tension will also act what? Straight downward. Because tension is going to act away from the load, right? Away from the load, so it's straight downward. So tension is also acting straight downward. Then if both of them are acting straight downward, then the centripetal force on this body is going to be the sum of the tension that is feeling plus the weight of the body. Is that clear? The weight of the body. Okay, so what will tension be now? So tension therefore is going to be equal to what? Bring this guy here, that will be Fc minus W. So T therefore becomes mv squared over r minus mg, which can change to T being equal to m is common between v squared over r minus g. Is it clear? All right, so it's just acceleration minus acceleration. Do you understand? All right, so that's tension here for you. Now, how about at point D? Now, at point D. Now, at point D, let's analyze. The tension is going to be acting where? The body is now down here. The tension will act upward still. Centripetal force is acting upward as well because always towards the center. But the weight of the body is acting downward. And remember, I've told you when a force is acting in opposite direction, when two forces are acting in opposite direction, you subtract. If you pick one force for positive, one direction for positive, you pick the other direction for negative. Is that clear? So tension, we have been picking inward for positive. So downward should be negative. Is that clear? So, and if you change it either way, you will get the same answer, okay? So the centripetal force that this body will feel towards will be equal to the tension that is in direction of centripetal force. And of course, it makes sense to choose upward for the direction for positive because it's centripetal force we are trying to analyze here. So tension will act inward, but weight will act downward. Therefore, from here, weight will come here, so that tension, because it's the tension we need, right? Tension will be equal to the force, centripetal force, plus weight. So tension therefore becomes mv squared over r plus mg, or T equal to m into bracket v squared over r plus g. So what does that tell you? That tells you that the tension is maximum where? At point D. So the tension felt on the string is always maximum. Tension is always maximum for vertical circular motion. So tension is maximum on the string at lowest point of displacement in the circle. In the circular motion, in the circular path. Okay, so please excuse me. All right, so let's continue. I've gathered some 10 questions. I quickly gathered 10 questions for us, 9 actually, 9. So let's use these questions to, um, validate the equations that we have, I mean, it's not to validate them, it's just to use those equations to solve these questions. The first question says a car moves. So you would have to be writing with me as I'm writing so that I'll maybe pause because I have only this place to solve. A car moves round in a circular track of radius. So question 1, the radius of the track is what? 0.5 meters. Is there a calculator? Let me get a calculator because so of radius 0.5 meters. 0.5 meters at 6 revolutions per second. Okay, so what does revolution per second mean? That each second 6 revolutions. Is that frequency or period? It's talking about how many revolutions per period. So that is going to be what? Frequency. Is it clear? That's frequency. So the frequency is 6, basically. 6 hertz. Now it now says you find the angular velocity V, angular velocity omega, omega, we're looking for that. The period t, okay, you can see already, we're looking for the period, and the speed of the car, v, also unknown. So we can begin to use our equations. We know that we're given r here. Now we know that omega is equal to 2 pi f. Also, I was able to show you this, right? So we can say that omega therefore can be equal to 2 pi times f, which is in this case 6. So 6 times this, omega will equal to what? 12 pi or 12 pi radians or 12 pi will be equal to 37.69. That's 37.7. 37.7 radians per second. 37.7. So that's the omega. Now let's find period. Period t is, you could also use this formula and say omega is equal to 2 pi over t. You remember this equation? So that omega is equal to 2 pi over, you have gotten omega now. You understand now? So period, you cross multiply period will equal to 2 pi over omega. Do you understand now? So you could use that. So t therefore becomes 2 times pi divided by 37.7. So 2 divided by answer is 0. So pi now divided by pi times answer. So the period is 0.167 approximately. Okay, seconds. Okay, so that's the period. That's the period. And it makes sense. Do you agree with me? It makes sense. If it's completing 6 revolutions in 1 second, so it means to complete 1 revolution, it means very, very, very much less than 1 second, which is 0.167. So that makes sense. So how about the V, speed of the body of the car? V is r omega, you remember? So if that's the case, then V becomes radius, which is 0.5 times omega, which is 37.7. This becomes 37.7 times half. That will be times 0.5. That will be 18.85. This will be meters per second, because it's velocity, meters per second. All right. Then question 2 then. Question 2 says that what is the velocity of a body moving in a circular path uniformly at so all this motion that we just talked about is for a body that is moving in a uniform circular path, because that analogy I gave you is not so regular because it's changing the path. But if it was moving, we are dealing with the ideal case where the circular path is uniform and regular. So it is moving in a circular path uniformly at that velocity. So I'm guessing that will be what's the velocity of the body? Moving at 3 meters. Let me see the question again. Where did I write this? Okay, per second square. Maybe it's second square. Maybe this is acceleration. Okay. A equal to 3 meters per second square. That's the linear acceleration. I'm sorry. With radius of that, r equal to 0.7 meters. In answer, we should find the velocity of the body. So recall that A is v squared over r. So I'm looking for v. So v squared will be equal to the square root. V will be equal to the square root of AR. Exactly. So V equal to square root of A, which is 3 times R, which is 0.7. I hope you understand what I did here. Simply make V subject of formula, you cross multiply, V will be equal to the square root of AR. So V becomes the square root of 3 times 7, 2.1. V equal to the square root of 2.1. That's 1.449. That's 1.45 meters per second. All right. That's number 2. Number 3 says that a particle of mass 10 kg, a particle of mass 10 raised to the power minus 2 kg. The mass of the particle is 10 raised to the power minus 2 or 0.01 kg. Is fixed to the tip of a fan blade, yes, which rotates with angular velocity of 100. Angular velocity omega is 100 rads per second. Now you will notice what I just told you now, that the fan blade is long. I mean, I'm saying that that body is attached to the tip of the fan blade. So the body, the fan blade, let's put the fan blade like this. So the body is attached to the tip. So this angular speed, you would think is not applicable for this body. Everywhere along like this, the omega is omega is the same. Exactly, that's what I was saying there. So even if I put the body here, omega is the same. I put the body very close to the pivot, omega is the same. Is it clear? So that's why I can write the fan is rotating at that distance, then it means the velocity of that particle attached to the end of the blade is the same thing here. So now if the radius of the blade is that, the radius of the blade is 0.2 meters from the pivot, calculate its centripetal force. So centripetal force is equal to m times a, which is v squared over r. So now we don't have v here. So we can get v, or we use the second equation, f sub c equal to m. You know we can derive it from here too. This is r omega all squared. R cancel r, then we have mr omega squared. So f sub c becomes m, which is 0.01 times r, 0.2 times omega, 100 squared. So this becomes 0.01 times 0.2 times 100. Let's just use 100 squared. If you square 100, that becomes 10,000. So 1, 2, 3. 1, 2, 3. 2 times 1, 2 plus 10 times 10, 20. So the answer is 20 Newton. All right. So that's that for question 3. Now let's go to question 4. So I would like to clean the top now. So question 4 says that a motorcycle of mass m equal to 100 kg moves round in a circle of radius r 10 meters with a velocity of 5 meters per second. This is going to be a very simple question. 5 meters per second. Find the coefficient of friction. Find the coefficient of friction between the road and the tires. Okay, so it's quite different. Now, I've not showed you this. Okay, so if the motorcycle, okay, now watch. You see, find the coefficient of friction. See, the frictional force, the centripetal force, is going to be equal to the frictional force on the tire. The centripetal force that is dragging the tire and the body, the body is on the tires, is dragging the entire body towards the center, right? For which reason the motorcycle is able to engage in uniform circular motion, which is I don't know how possible that is, but that is the ideal case. So that frictional force is going to be equal to the centripetal force, the frictional force that we felt under the tire, between the tires and that. And what's the formula for frictional force? Remember, is equal to mu r, mu normal reaction. But this body is not on a bent road, right? So for a body on this surface, if this is the tire, okay, the tire will look like this, something like this. Then the man seated on it like this. I don't know, just manage it. So this place, R will be exactly equal to mg, weight of the body. So if that's the case, then we know that our frictional force is equal to mu mg. Mu is the coefficient of friction. So if that be the case, then the centripetal force Fc equal to what? Mu mg. Alright, let's now go on to solving it. So we are not giving, okay, it's mu we are looking for. We have m, we have g will be 10 meters per second squared. So we are giving Fc. So Fc is mass mv squared over r is equal to mu mg. M cancels m, right? Okay. So this even proves something to you that, do you remember we had v squared over rg to be tan theta? So that will be the coefficient of static friction as well. Good. Alright, so v squared now is 5 squared over r, which is 10 times 10. So that will be 25 divided by 100. That will be 0.25. 0.25, what will be the unit of static friction? Unit of coefficient of static friction. Force over force. It doesn't have a unit. So the answer is 0.25. Is it clear? 0.25. And this even validates it. It doesn't have a unit because it's meter times meter over second squared. Then meter per second all squared. This is meter squared over second squared. Everything cancels out. Is it clear? Alright. So you can see the consistency of physics now. This is very consistent. The very fine science. Now for the next one, number 5. A force F is required to keep a body of mass 5 kg moving in a circular path of radius 3.5 meters. 3.5 meters at a speed of 7 meters. Is 7 meters per second rather. What is the speed if the force is tripled? Okay, we triple the force. So normal F sub c is mv squared over r. So if we triple this, it's just tripling the answer now. Okay, we are looking for the speed. What is the speed? Okay, so normally the Fc is going to be m v squared now. M, which is 5, times v squared, 7 squared over 3.5. That is 5 times 7 times 7 over 3.5. Here 1, here 2. 5 times 7, 35 times 2, 70. So F sub C equals 70 Newton. Now we triple the force. 3 times 70 is what? 210. So 210 is equal to the same mass, 5 times v squared now. So the same FC has been tripled, so it should be equal to the new m. M is not new, but v is now new. So v squared over the same radius. The radius has not changed. So what do? We cross multiply. We have 210 times 7 equal to 5v squared. That size by 5. Here 1. Here 5 into 10. That will be 4. 1. Here is 2. So 42 times 7. So v squared will be equal to, yes, 42. So v squared will be equal to 47. That's 42 is 6 times 7. So that's 6 times 7 times 7 over nothing. Okay, so take square root of both sides. So that becomes v equal to 7 root 6. That's the answer. Let's use calculator, please. 6 times 7 times 7. So square root of 294. That's 17.115. 17.1 or 146. Okay, so that's question 5 for you. Now let's go to question 6. It says a particle. It says a particle of mass. A particle. What is it? Number 6. A particle of angular speed. Angular speed is 8 pi radians per second. Moves in a circular path of radius that. Calculate the magnitude of its frequency, the magnitude of its acceleration. A equals unknown. Very simple. Recall that A equal to, we did A equal to v squared over r. So by the time we see y equal to v squared over r and v equal to r omega. So A equal to r omega all squared over r, which is equal to r squared omega squared over r. Do you understand now? That is r omega squared. I think I proved this. So A equal to r omega squared, that's just the answer. 2 times 8 pi. I'm not changing pi. So that'll be 16. This squared, So that'll be 64 times 2, 128. 128 pi squared. Pi squared radians squared per second. Radians per second squared, rather. Radians squared per second squared, I think. What will be the unit? Let's get the unit. Radians squared. These radians are per second squared, yes. Okay, or radians meter per second squared, okay. This is radians per second. So it's squared, radians squared per second squared. Meter, radians. This is for linear, so we have to put the meter here. Radians squared per second squared. Alright, I'll verify what that is. Now number 7. If the moon revolves the earth in a circular path of radius, this 3.85, is that the radius of the earth? No. And makes a complete revolution in time. Okay, complete revolution, that will be period. Okay, take note of that. Complete revolution, period. That's 27.3 days. You have to convert this to seconds. So days, that will be 27, convert to hours. 27.3 times 24 hours. That will tell you how many hours that these days represent. Then times, convert hours to minutes, 60. Convert minutes to seconds, 60. Is it clear? So this becomes 27.3 times 24 times 3600 equals 235,58720 seconds. Okay, that's period. Now what do we do from here? So it now says, where is it? Determine the centripetal acceleration. So A, centripetal acceleration of the moon towards the earth. So what is A? A is V squared. No, A is R omega squared. So let's use that. Okay, recall, now what? Please follow me. Recall that omega is 2 pi over t, right? Substitute this into this equation. A becomes R times 2 pi t all squared, 2 pi over t all squared. So A becomes R 4 pi squared over t squared. So this is the formula we use. This is not hard. So R times 4. What is R? 3.85 times 10 raised to the power 8 times 4 times pi squared. Let's leave pi as pi. Then t squared. That will be Jesus Christ. D squared again. Alright. So that will be 3.85 times 10 raised to the power times 10 raised to the power 8 divided by 2358720 is equal to, then that times 4 is equal to 652.89. That's 9.9 pi squared what? Pi squared acceleration meters per second squared. Is it clear? Since this thing is in meters, the reason why I put radians is because I use pi. Okay? So since I left pi here, I should still put radians. Pi radians squared meter per second squared. Radians squared meter per second squared. This is where it's supposed to be. Radians squared meters per second squared. Alright. So let's go to the next one. That's the second to the last. Number 8. Number 8 says, now, in the meantime, make sure that if you need questions, both O-level and A-level questions on this thing, you can reach out to me. I have an archive of many questions on this, so make sure that you reach out to me on my WhatsApp number 09021416307. I mean, for international 2 plus 234 90214163. So question 8 says, an object of mass 10 kg, the mass of the object is 10 kg, is whirled around in a horizontal circle. Here, we've gotten to horizontal circle now, of radius 4 meters. Radius is 4 meters. By a revolving string inclined to the vertical. So the revolving string is inclined to the vertical, has radius. If the roll inclined to the vertical, if the uniform speed v of the object is 5 meters per second, calculate the angle of inclination. This is very simple. Recall that tangent of theta is what? V squared over RG. I proved this, right? So theta becomes the tan inverse of what's V squared? 5 squared over R, 4 times G, 10. Okay, we don't even need the mass here. We don't need the mass for anything. Or do we? I don't think we need the mass for it. Okay, yeah, I think what that equation proves. Remember that equation, we did tan T sine theta is F is here, T, FC. Okay, so that's mv squared over R. So mv squared over R dot mg. Okay, what this equation proves is that the angle is independent of, can be independent of the mass. Okay, okay. So we don't need the mass, all right? So this becomes 25 over 40 as 5 over 8. That will be 0.625. Oh, sorry. So theta will not be tan inverse of this. Sorry. Theta will go to tan inverse of 0.625. Okay, I wrote nonsense here. I'm sorry. Shift tan of 0.625 is theta equal to 32 granotes. That's the answer. 32.00. The next one, number 9. Let's solve number 9 here. Number 9 says that an object of mass 0.3 kg is whirled round in a horizontal circle of radius this. Mass is 0.3 kg, is whirled round in a horizontal circle of radius that. The radius of the circle is 0.8 meters. By a string inclined at 30 degrees, so we have theta is 30 granote. Calculate the tension in the string. Very simple. Tension in the string. Simply recall that, I just wrote it here, that T sine theta will be, if Fc is here, T is here, weight is here. So T sine theta will be opposite over hypotenuse. That is Fc, right? So T will be equal to Fc, more like say T sine theta. We can even use weight now, T cos theta too. Remember that T cos theta is also okay, since we have MV, the tension of the string, okay. So T sine theta is also, T cos theta is also W adjacent over hypotenuse. So can use mg here. G is 10 meters per second squared. So are you following? So from here we can say that, let's use any of this equation. I think this one is easier. So tension is going to be equal to mg over cos theta, cos 30. So T equal to m, which is 0.3 times 10 over cos 30. That's root 3 over 2. So T equal to 3 divided by 3 times 2 divided by root 3. That's 6 over root 3. Now by the time you multiply by root 3 over root 3, you get 6 root 3 over 3. So the answer is 2 root 3. I rationalize there. You can use calculator directly, you get the same answer. So that's the tension in the string in Newton. Tension is a force, so it's in Newton. And the last one, let's calculate the last one here. The last one says that the speed of the mass in the horizontal circle, the speed of the mass. Remember that, okay, this is where we need t sine theta. So t sine theta is mv squared over r. Okay. So we are perfectly okay. So we've gotten t now. So that will be 2 root 3 times 1 over 2, because sine times sine 30 granite is equal to m, which is 0.3 times v squared over what is r? 0.8. And I was looking at, okay, let's just continue. Bring this guy here. More like, cross multiply, you get v squared is equal to this times this. That's 2 root 3 times 1 over 2. Sine 30 is 1 over 2. Then times this 0.8 when you cross multiply. You now divide both sides by 0.3. Is it clear? Divide, because if you cross multiply, this one is still equal to 0.3 times this guy. So by the time you divide both sides by 0.3 and 0.3, this takes care of this. So that v squared will be equal to the square root. I have to take square root now. So we have root 3 times 0.8 divided by 0.3. So v will be equal to the square root of root 3 times 0.8 divided by 0.3. Let's use our calculator now. Root 3 times 0.8. Then divide by 0.3. And square root of this is 2.149. So that will be 2.15. So v equal to approximately 2.15 seconds, meters per second. So that will be the answer. Now, I said I won't leave you without showing you this. Let's say an object, a car, banking. Let's talk about banking. No worry, I'll write that number again. You can reach out to me on. I have up to like 50 questions for you to solve on this thing. 50 questions. It's impossible that you solve 50 questions on this topic and you will not master it. You will not have mastered this topic. So, and I was like, okay, banking now. Banking of a road. Now, because when they create roads on hills or mountain edges, they tend to bend the road towards that mountain, so that if the car drifts, the car will still be drawn towards the center. Do you understand? Now that's the use of centripetal force. They use it in banking of road, so that if there is a cliff, if there's an edge that it can fall off, whatever happens to the car is always going to be tilted towards the center, so that it will not fall off. Is that okay? Yeah, I remember one war that we fought that time. So we were, fighting. So I was just driving the car, and then someone just did something. Launch a bomb. That's how I just went. I just drifted, and the car I flew, and then that centripetal force kept drawing me, and then I came back to the road. All right, so let's say the road is banked. I said to be created at an angle. If this is the normal ground surface, the road will be banked at an angle theta, usually very small. So my one is too large. Something like this, so that the car will be moving towards like this. If this is the mountain, now let's assume this is the mountain. So if a road encircles it before it joins another road, to be banked. Is it clear? So let's say this is you, or maybe your dad in this car, for example. To manage my car, I don't know if it looks like a car, but it should look like a car, If it doesn't look like a car to you, draw your own in your book. And this will be your big head. So These are side mirrors. These are supposed to be side mirrors. Okay, I think I should do it. Okay, so this road is banked at this angle. This tire should touch the ground. Now, watch. For this car, for a bike, let's do for both a bike and the person and the car. The bike and car. See, this bike one is it's just somehow. I don't know. Manage it. Just manage it. This must be your bike. Doesn't even look like it. So let's say a bike is also here, a bike. Just draw the tire. The reason I'm drawing just the tire is because it's only the tire that I need. Okay, because there is a force that is going to be acting between the surface of the ground of that asphalt on the ground and the tires of the vehicle. So if that is the case, what will be the magnitude of that force? Now we know there's going to be a normal reaction. Sorry. So normal reaction we act at an angle, and here it's going to be two normal reactions. There'll be one here, and there'll be another one here. What we act straight downward from the center of gravity of the distance is weight of this guy, or weight of this guy. We act downward. So let's analyze for this guy. According to what we did this other time, we know that the force that this guy will feel, which will cause centripetal, at the base here to be frictional. So mv squared over r is going to be, now this road is banked. Sorry, this road is banked. So the frictional force is going to be mu r, like we said, but r now, the normal reaction is going to be, if we analyze the vectors, we have at an angle like this, and we have our normal reaction like this. We have mg this way. So what we'll do is we'll try to resolve this guy here. Now it is always such that I've done this before. This angle here is the same as this angle that the car will bend, at which the car will bend. So if it's the same, then mg that is acting downward, we'll resolve it here to get r, to equate it to r. Then r will be equal to mg, where cos theta. It should be cos theta. Yes, r will be mg cos theta. So, are you with me now? So if that's the case, then our equation here becomes mv squared over r. Mv squared over r is equal to mu r, which is now mg cos theta, mg cos theta. M can cancel m. So v squared over r is equal to mu g cos theta. So mu will be equal to the variable side out with v squared over rg cos theta. Velocity, of course, from here will be equal to r mu rg cos theta square root of that. That will be the velocity. Is that clear? Then for this body here, the centripetal force will be drawn towards the right, towards the center. So if that be the case, centripetal force is here. Let's analyze that. Centripetal force is here. We didn't analyze centripetal force here. Centripetal force here now will be equal to, we've done this, okay. You can use this equation to get centripetal force. So mu mg cos theta, mu mg cos theta. So in the same way here, the only difference here is that it's going to be R1 plus R2 here, mu R1 plus R2. Exactly now. Cos theta equal to FC. You know, this is the only dynamic that changes. Do you understand? You know, it's mu R cos theta, mu mg cos theta. Exactly. Provided that where R1 plus R2 are mg1 plus mg2. Exactly. So, and then you might now ask me, Master, why are we putting R1 and R2? That can the normal reaction not be the same? If it's the same, you put R. But it can feel different R's, normal reaction, yes, depending on the type of tires they use. If the tires are the same size, they are, do you understand that for many reasons the R might be different. Okay, so those are the different equations you can also use. So this will be the end of the video. Do what to subscribe to the channel. By the time I give you questions, so understanding what I just taught you here, you can solve any question. Reach out to me on my WhatsApp number. All right. God bless you as you subscribe to the channel.